In exercise 10D, I'm not sure if you would have picked it up or not, or made the observation that each time you differentiate, the degree, which is just the highest power, in the expression decreases by 1. Now, if you think about that, and you start off, say, here with this expression, the first derivative of that will have x to the power 6. Then the next derivative's highest power will be x to the power 5, and then 4 and 3 and 2 and 1. We'll rarely deal with functions like x to the 7th. That'll be extremely uncommon. As you can see here, it says that we mostly just focus on first and second derivatives only. And you also see that the original function it usually is nothing much more than a cubic, x cubed, which means if your function, for example, has x cubed as the highest power, you know that f dash x will have x squared as the highest power, and the second derivative will have x as the highest power, and if we were to differentiate it one more time, you would have a constant, straight out constant. Now, in realizing that and thinking about more so, not so much the cubic, but what the quadratic looks like. We know a quadratic looks like that. We know linear, x to the power 1 is called linear. It looks like that, or it looks like that. The next derivative then would be a constant. So y is a constant, which is a horizontal line. And then after that, so the fourth derivative would be 0, no gradient. The reason that it's good to think about what these functions actually look like is it will help you quite a bit in this next exercise, because in this next exercise we're going to be observing whether the second derivative in particular is a positive, whether the second derivative is a positive number, or whether the second derivative at a particular point is a negative value. If we got to our second derivative and it was a horizontal line, then we can easily see if that horizontal line is a positive number, like y is equal to 3, or if it was if our second derivative ended up being a negative number, like y is equal to -1, then it's very easy to see, yes, the second derivative was always positive or it was always negative. And what is the significance of knowing whether the second derivative is a positive or a negative? It tells us about the concavity. So that's what we'll be focusing on, the concavity of the original curve. Now, we work out the concavity at a particular point, and that particular point we've just abstractly named as A. So this actually says the value of the second derivative at some x value called A, if it is a positive, it ends up being positive. So you've substituted some x value into your second derivative, and you've evaluated that and you've come out with a positive number, then what it means is that at x is A, the graph is definitely concave up. And then the opposite situation, if you have substituted this value, we're just calling it a at the moment, but if you've substituted x with a number into the second derivative and it evaluates to give you a negative, then what you know is that at a, the original curve was concave down. So concave up just means, scooping up. This part of the curve is scooping up, and this part of the curve is scooping up. This part of the curve is scooping down, and this part is scooping down. So we call those concave up, concave down. This cubic graph has sections where it is concave down, and then it switches and becomes, let's go a different colour. It switches and becomes concave up from thereafter. So you can see it is good to know at a particular point whether we are concave down in our shape or we're concave up. And when it changes concavity, we have this point of inflection. A point of inflection is a change in concavity. And you'll see later when we focus a little bit more, again, on points of inflection, that you'll see that you must show that concavity changes. From this point, previously, and as you can see here, because this is concave down, your second derivative would have been a negative. And then you test a point just the other side of where you suspect there's a point of inflection. And if you check the point just to the other side and it's then concave up, you've had a change in concavity. From concavity being down to concavity being up. And you can conclude, without drawing your graph, that you've got a point of inflection. We're just going to see what it looks like graphically. So on our original function here is a quadratic, and we know that for our quadratic, our highest power is a 2. So we know with our derivative, our highest power is going to be a 1, and then we can see with our second derivative, we will get a constant value. So on this original function, it looks like a basic y equals x squared. We know that when we look at the derivative, and now, to be honest, I shouldn't have any scale on this axis because I don't know exactly the value of the derivative because I don't even have the exact function or the complete function. I can see it was an x squared, but it could be, 7/8 of x squared. And 7/8 of x squared would probably look like y equals x squared to the naked eye. But without that additional information, I can't really evaluate the gradient anywhere. But what I do know about the gradient is, what I know about the gradient is at this point, the gradient is 0. So my first derivative is definitely going to go through that point. Prior to that, the gradients were negative, and steeply negative, negative, not so negative. So quite negative and not so negative. And thereafter, a little bit positive, and then quite positive. So it's going to go on like that. We know that it's going to be a straight line because we know things like the highest power decreases by 1. When we differentiate. And if I'm graphing a linear, I get a straight line. Now, things we know about that straight line is it has a constant gradient and it's a positive number. And again, I should not have any values on here because I can't tell you exactly the positive value of the gradient. I can just say that has a positive gradient. The gradient doesn't change. Let's just say this is it. Goes through here. this is the graph of the second derivative. It's a positive value, and I'm not going to assign any value to it. So what can you see here, hopefully? That the second derivative is always positive. It doesn't matter what x value, it's always this constant positive number. Now, what connection is that back to the original function? Well, this function is always concave up. We saw that just back in the notes. Always concave up. Always concave down. And again, this is a something x squared. When you differentiate, you'll get linear, a decrease by 1 in the power. And then again, you'll get a constant for the second derivative. This is always concave down. Not really focusing on the first derivative, but the values are quite positive, less positive, less positive, less positive until a 0. So in this region, quite positive, less positive until we get to 0, and then the gradients go negative. Now, that's a straight line, it's linear, we know it has a constant negative gradient, and again, really, I don't want those values because I just want to be able to say it's some negative value. That gradient is a negative value. So it's always negative, and what connection are we going to make between this second derivative and the sign of it back to the original function? If the second derivative is negative, your graph is concave down. And for this one, what do we know? I think I'll just pause the video or I'll run out of time. Okay, with this third example, which is a cubic, you can hopefully see that there is this first section, and I'll call it the first section till there, till about x is 2, is what we would call concave down. Then after that point, we have a change in concavity and it goes concave up. Now, we're really interested in the second derivative, aren't we? Because the second derivative should show something happening at 2 and hopefully some negative values for the second derivative, because concave down means second derivative is negative. So a negative value for the second derivative up until 2, then a positive value, positive values for the second derivative. We know this is a cubic. The first derivative will be quadratic from 3 down to 2. It's showing that sometimes the gradient was positive. Yes, it was. And then the gradient was 0. Then the gradient was negative. Then the gradient was positive. Like I said, it's not so much that one that we're interested in. It's now this second derivative. So we're getting the gradient. Now the gradient of this is negative all the way to the significant point is 2. And the gradients were negative, so my line is negative. And after 2, all the gradients are positive. So that's what I'm graphing. Now, it's not so much the connection between the second derivative and the first, but the second derivative and the original function. We can see here, this is my graph of the second derivative. And again, I shouldn't have any values there. Significant point is occurred at 2. At 2, anything before x is 2, I've got negative values for this function. It's below the x-axis. The y values are negative. What do I know? That if the second derivative is a negative, it should be concave down. So is it concave down all the way to x is 2? Yes, that's exactly what's happening. It's concave down all the way to x is 2. And thereafter, it's positive. And you can see the graph is concave up after that. I'll have to stop the video right now.